We've essentially discussed so far what I refer to as the differential calculus. Now we're going to jump into something completely different called the integral calculus. Now I'm going to start off playing a silly little game of computing area, or at least approximating area. So here's what I want you to do. I want you to consider a continuous function, at least continuous over the interval from a to b. And what I'm going to do is I'm going to partition the interval from a to b. When I say partition, I just mean cut into smaller parts, but it's going to be a regular partition. I'm using the adjective regular like you did in high school geometry. It just simply means all those sublengths are of the same length. So let me also refer to A as x naught, x1, x2, all the way down to an arbitrary I subinterval, x of I minus 1 to x of I, down to the very last interval from x of n minus 1 to x of n, which is just b. So I'm trying to approximate the area beneath this curve as x ranges from b to b. Now to do this, I'm going to pick a value of x in the first subinterval. How about x of 1 asterisk? Now, I don't care how you choose x1 asterisk. It can be the left endpoint, it could be the right endpoint, it could be the midpoint, it could be any value of x in between x0 and x1. In the second subinterval, I'll choose an arbitrary x value. I'll call it x2 asterisk. In the I subinterval, x of I asterisk. In the last subinterval, x of n asterisk. Now, I'm going to use those x values to go straight up to the curve. To determine the height of an approximating rectangle. Now, if I choose x of I asterisk, that is to say all these x asterisk values as the left endpoint of each of these subintervals, then I will be using what I call the left endpoint rule with n subdivisions that approximates the underneath the curve. I could just as easily choose x of I asterisk to be the right endpoint, and if I have n subintervals, that will approximate the underneath the curve. I'll get to an example of such in just a minute. So let's see if you and I can approximate the area underneath this curve from the interval from 1 to 3 using, I don't know, how about just 4 subintervals, and we'll use the left endpoint rule. So I do think the area underneath the curve as x ranges from 1 to 3 is approximated by the left endpoint rule of 4 subdivisions. So here's dividing the interval into 2 parts and the 4 parts. Notice the width of each of these subintervals, I often refer to as delta x, is nothing more than the length of the full interval, divided by how many subintervals I have. In this example, A and B are 1 and 3, and I have 4 subintervals, so of course the length of each of those subintervals will have. Clearly you can see that the way I created the ticks. So if I use the left endpoint to go straight up the curve, draw my first approximating rectangle, it'll have area 0. But here's the left endpoint of the second subinterval going up to the curve, there, there, there. So I think the left endpoint rule gives me f evaluated at the left endpoint of the first subinterval times my delta x plus left endpoint of the second subinterval, third, and fourth. I'll pull out the delta x, which in this example is just 1/2. Here's f of 1. Here's f of 3/2. F of 2. F of 3/2. Sorry, should that be at 5/2? My apologies. I have no idea what that is. Is that the natural log of jeepers? 15/2 times 1/2. Now, in approximating the area using the right endpoint rule, I'm running out of room. Can I do this? I'll slide this value up. Now, in using the right endpoint rule, with my red pen, At the right endpoint of each of these 4 subintervals, I'll go straight up to the curve to generate the height of that approximating rectangle. And I think, numerically speaking, that's going to give me the following. Or how about this? Pulling out the delta x. Now, what is left over? So is that a 45 over 2? Now, everybody, this happens to be a strictly increasing curve. So I do think the actual area is somewhere between these 2 values. So I do think in this example, the actual exact area ends up being somewhere between these extreme values. But again, I just got lucky in this derived example because this function has to be strictly increasing. So the left endpoint will clearly underestimate the curve, the right endpoint clearly overestimates the curve. Now, notationally speaking, before I move on, let me suggest this. Sorry. These are rather far apart, relatively speaking. So I think for me to get a better approximation, I'll probably choose a lot more subintervals, just 4. So if I choose a lot of subinterval, I do think these 2 values get closer and closer to each other. I'll get a better approximation for there underneath the curve. I don't want to illustrate that here because I just think if you're going to have a lot of subintervals, you'd probably use technology to do the work for you. Now, can you imagine, theoretically, what would happen if I took the area underneath this curve to be approximated by taking the area of each of those subintervals, summing them together as I range from 1 to n? I think this will approximate the actual area underneath the curve. Now, the higher the value of n, more likely I'm going to be getting a better approximation, but it's still just a mere approximation. So let's see if we can't do better than this. So here I go. The area of the I subinterval is just length times width. Its length is delta x. Its width or height is the corresponding y value at that x of I asterisk. And so look what happened if I took the limit as I arranged from 1 to, gosh, I'm sorry, I didn't mean that, did I? I meant to say take the limit as my n increases without bound. That means the limit of this is eventually going to give me the exact area underneath the curve. So it looks to me like I'm getting to some fundamental definition of the integral calculus. But for now, I'm just taking things a little easy, suggesting that if we do allow delta x to go to 0, that is to say n increase without bound means the same thing, then theoretically speaking, that will represent the exact area underneath my curve. But I have to have continuity for f, at least continuity for all values of x from a to b, with the exception of maybe some n finite values. But I won't get into that. I'll maintain that f is continuous for all my examples. All right, I'm happy. I'm happy that I can start getting sophisticated.